Hello, and thank you for viewing this video regarding management of utility data in the face of the smart grid as it emerges across the world. Before going into the video itself, I'd just like to make a couple of comments. This video is not supposed or intended to be a promotional video selling Screaming Powers products and services. If you want information on those products and services, you can use the normal channels, which are basically the website, or just send us an email. The other thing I want to talk about is the intended audience. I've made this video as high level as possible so that it reaches the widest possible audience. Unfortunately, this means that if you're a utility professional and it's your day job managing data, you might find some of the information a little bit basic. On the other hand, if you're a pure layman and you've never come across the concept of data management within a utility before, you might find the information a bit daunting. But I've tried to strike a balance, and hopefully you'll get something informative and useful out of it. So into the video, what am I going to talk about? I'm only going to spend a minute or two on each slide, and the first one I'm going to talk about is the utilities view of the smart grid. And in our idea, the smart grid is basically just the overlaying of ICT, or information and communications technology, on top of what is predominantly a 100-year-old electrical delivery system. The next thing I'll talk about is the new landscape and how the smart grid actually affects things. I'll talk about the sources of data, both traditional and the new data that's coming in because of smart grid. And I'll talk about the data explosion, in other words, the volumes of data that utilities are going to have to handle. I'll move on to talk about the generation and movement of data, in other words, where does the data come from and how does it move throughout the systems. I'll then look at communications options. How do we actually move that data from the endpoint, the initial device, all the way through the enterprise and to the customer. I'll look at the concept of data concentration and the need for distributed processing. I'll look at the front-end processes. This is a gateway into the utility when the data reaches the enterprise. I'll look at how the data is used within the enterprise, and I'll look at how data can be delivered to consumers to empower them. I'll talk about some of the concerns that both the consumers and the utility has, and I'll draw some high-level conclusions at the end of the presentation. So firstly, the utilities view of the smart grid. This chart represents a survey that was done a few years ago, where just over 100 utilities in North America were asked what they regarded as important technologies from the emergence of the smart grid. The blue obviously is most important, the reddish brown is less important, and the orange yellow is least important. Across the bottom we can see the number of respondents out of the 100 plus utilities. Along the vertical axis we can see the different areas. And if you look at the graph or the chart, you can see that communications dominate, and the reason for this is that communications is what we call an enabling technology. As I said, the smart grid is the overlaying of communications technology on top of the traditional distribution system, and so without communications nothing works. The next highest rank is metering, and metering is something that can give the utilities a positive rate of return very quickly. Then they seem to concentrate on the more traditional technologies like substation automation, outage management, and to some degree demand response. And as we move more and more towards the consumer side, there's less appetite for the actual projects that constitute a smart grid in its entirety. And so things like home automation are barely on the chart, and other things like electric vehicles don't even make it onto the chart. But the basic thing to see here is that the utilities, unsurprisingly, are focused on the technologies that will give them a quick positive rate of return, and they can do that mainly through metering. They can see the benefits straight away. If we look at the new landscape, Across the bottom of the screen, we've got the different technologies, and to the left, we've got the traditional ones, such as plant controls, substation automation, feeder automation, etc. Then we've got the emerging technologies like microgrid control, electric vehicle support, and advanced metering. And over on the right, we've got the technologies that are further out into the future, like building automation. All that technology is supported by the ICT, so it has to go through a common infrastructure, communications infrastructure, into the enterprise. And simplistically, we've split the enterprise into 4 groups. Corporate operations, which are the business systems, such as SAP, business intelligence, etc. Real-time operations, which include the SCADA, system for control and data acquisition, demand-side management, outage management, and distributed resource management. We also have customer services, which include the call center, customer information system, billing, and the new meter data management system, and smart grid support. And then we have the enterprise support operations, including energy efficiency, maintenance, asset management, etc., etc. This diagram was actually requested by the Provincial Electricity Authority in Thailand, who wanted a simple view on how the new landscape would look as far as they're concerned as they move down their smart grid roadmap. But the point we're trying to make here is that we've got a very diverse landscape, and what we need to look at are the use of standards and interoperability to future-proof any of the technology that we actually put in place. Some technologies like computers move extremely quickly and get replaced within 5 years, whereas if you look at the primary equipment on the grid, their life expectancy is the order of decades. So what are the sources of data? We have the traditional sources of data from the current SCADA, system control and data acquisition systems, and that will continue. But then we have lots of new data coming from electronic metering in particular. And when we're talking about electronic metering, we're not just talking about revenue metering from consumers, we're talking about metering for public lighting, aggregated flows through feeders, net metering for distributed generation, vehicle charging stations, etc. So there's a whole host of new electronic metering data. We're getting new data from asset management systems and other business systems. As the enterprise deploys sensor technology, they're going to be getting far more information coming in. We're going to get data from the ubiquitous deployment of sensors to look at things like power quality, sort of voltage control, current, temperature, etc. We're going to get new data from consumers or customers as they let the utility have information on their home appliance usage. And we're going to get new data obviously from the new technologies as they emerge. And these include things like distributed generation, microgrids, electrical storage, electric vehicles, etc. We're also going to be able to derive a lot more data. When we combine this data, we can derive new data information such as power quality, analytics, etc. And we need to ask the question, why are we collecting so much data? Well, the reason is, as one prominent engineer once said, you can't control something you can't measure. And the whole idea of the smart grid is that we have better control, better measurement, and we can wring out better efficiencies from the systems. So what about the volumes of data? We've seen that we're going to be getting new data from all kinds of different sources, and this will mean that we've got orders of magnitude more data coming into the utility. And there's a possibility that if we don't change the processes and the systems, we're going to end up with data overload. Just one example, electrical metering for the consumer. Traditionally, the utility only did one consumer value, acquired that per month per customer. In other words, 12 values per year per customer. If we're looking at interval metering, time of use metering, at let's say 15-minute granularity, that means roughly 3,000 times more data per customer per month. And that's only if we read one particular parameter, in other words, active energy. What if we also want to read things like voltage, current, frequency, volt amps reactive, meter status, in other words, has the meter been tampered with, etc. And what if we want to set outputs for things like remote disconnect in the event that a premises gets made vacant? Well, what this means is that we'll be drowning in data, but we're thirsty for information. We will have streams of data coming in, but unless we can turn that into meaningful information that people can understand quickly and make use of, then we're basically missing the whole point. Now let's take a quick look at where all this new data is generated and how it moves through the system. Of course, one of the primary sources of all this new data will be from electronic meters, and we can have different types. And then we have the primary equipment already in the field, such as transformers, substations, reclosers, etc. And all that data is traditionally brought in via the SCADA system. But we have new sources of data in terms of distributed energy resources as a consequence of the smart grid. And this includes things like renewable energy, wind and solar, plus microgrids, vehicle charging, etc., etc. First thing we need to do is acquire this data locally, and to do that we have a thing we call last mile communications, and this basically hooks up the end devices and gives a primary path into the system. Next we need to put those through data concentrators because of the sheer volume of data, and the data concentrator will perform additional functions which I'll talk about in a minute. And then from the data concentrator we need to get it to the enterprise through a thing called a front-end processor. And this is basically where all the data from the different data concentrators and all the devices comes in. The front-end processor to data concentrator is called the backhaul network, and in a lot of cases this is already in place via the utility. And we then end up within the enterprise where we're using LANs, and we have to get the data from the front-end processor onto those LANs. The first LAN is the enterprise service bus, which is a slow speed bus, and we have low data rates of typically minutes or hours characterized on that bus. And we also have a high-speed bus, which is the operations, and here we need the data to be fed into the enterprise or into the operations side every let's say sub 1 minute, 30 seconds, 15 seconds, whatever. Then we've got this new concept that some utilities are looking at of mobility apps to their consumers and also to their mobile workforce, and of course that goes to the internet cloud output via a firewall. What we're seeing here though is that we have many sources of data, and we need one corporate strategy on how we're going to handle that data within the enterprise and get it out to the consumers and the people that need it. We have a quick look at the communications options. I'm not going to spend a great deal of time on this, and I'm not also going to talk about the corporate LANs. I will talk though about the last mile communications that we've just mentioned, and the data concentrators into the backhaul network. So last mile, we have things like power line communication, radio mesh, which is in the license frequency, typically less than 1 gigahertz. We have 2G and Edge, which is public networks, and actually could become quite important because as the telecommunications companies roll out LTE, 3G, 4G, etc., these 2G networks are underutilized, and so they're looking for customers for them. We have unlicensed radio such as Zigbee, and we have more difficult technologies like broadband over power line, spread spectrum radio, and hybrid fiber coax, plus a host of others. I won't go into them all. As far as the DCU to the backhaul is concerned, direct connection onto the backhaul network is preferable. So if we can connect directly to a router on the backhaul network, that's the way to go. We can also use public networks, and here we can use 3G and 4G LTE. We need higher capacity than 2G because of the data volumes. We can use WiMAX, of course, and we can use copper in the form of asynchronous DSL or synchronous DSL. And we can also use private comms. The utilities sometimes have their own private networks, and they can be things like GEPON, which is Gigabyte Ethernet over a passive optical network, private wireless, such as the systems that people like Trilliant and Silver Spring roll out, fixed serial, fixed copper on protocols such as Modbus, and they can also have their own radio systems, such as the multiple access radio system, but here we're limited on the data flows and the actual license pairs that the utility can buy. And again, the thing we're trying to say here is that we have lots of options both on last mile and from the DCU to backhaul, and there's no one-stop shop. One size does not fit everywhere, and in fact the utility will be using a mix of different technologies to get the data to where it's got to go. If we look at the data concentrators again, not spend a lot of time, but Screaming Power has its own view on data concentrators, and we see them as necessary because the volumes of data increase dramatically. Again, if we look at the metering example, traditionally the utility read 12 meter reads per year per customer, and now with AMI at 15-minute granularity, we've got more than 35,000 reads per customer per year, and that's only on active energy alone. So the central systems cannot possibly cope with acquiring this data from every individual device, and they've got to come through concentrators. The data concentrators should be able to store the data locally, of course acquire the data from any device connected to it, store it locally, filter, compress and only transmit data when necessary, so it doesn't move unnecessary data around the system. The data concentrators also need to act as protocol converters, for example ZigBee at the last mile to WiMAX into the backhaul, and it can also act as a firewall, etc. It can acquire data from multiple sources simultaneously, including metering, public lighting, vehicle charging, primary field devices, and on different protocols simultaneously. And it should acquire data for different commodities. This presentation is predominantly focusing on electricity, but some of the techniques and concepts are equally applicable to gas, water, and we can even collect weather data, which is a common requirement across utilities. And again, the point here is that we should make use of distributed processing. The data concentrators are mini computers or microcomputers in their own right, and we should make full use of them. And just continue along this vein. If we take the premise that we're going to use a distributed processing regime, we should perform all calculations locally, we should do alarm and event handling locally, we should do local historical storage in short term, and by short term I'm talking in terms of months or sub year, and we should do filtering, and we could even do control via the data concentrators. The data concentrators need to supply data to different systems under different scenarios. Some systems require the data concentrators to be polled, others would like to acquire the data by exception, in other words when something has changed, and some others on demand, in other words just sit there and wait until I ask for a file, and that will then be passed. But the point is that the acquiring and data forwarding could be at different rates within the concentrator if we get the design right. So for example, AMI revenue values could come in every 15 minutes into the enterprise if that's what's necessary, but the same values could come in every 30 seconds when we're just looking at things like voltage or power consumed or frequency or whatever. The data concentrators also need to be fully customizable, because as the smart grid designs shake out, there'll be new requirements and different applications and different processes required of them. And they must be fully integrated. They've got to be single board computers with no moving parts, suitable for the environment in which they're in, and they should be cheap. We're talking a few $100s, no more. They should be low power, so they don't consume any real current from the network, and also don't generate a great deal of heat. And they should support open standards and protocols. And again, the point we're trying to make here is that use the power of distributed processing and only move the data to where it's needed when it's needed. Now let's quickly look at the front-end processors. Some AMI vendors refer to these as head-end systems, But when they talk about head-end systems, they're really talking about data concentrator functionality. In other words, they're receiving streams of digital data, and then they convert it into a common form to be moved within the enterprise, and they don't typically do much more than that. So the AMI vendors see the data concentrator more as a merging unit, and they let the head-end systems perform the tasks of the actual data concentrator. But we believe that the head-end systems should be a lot more. They should be able to handle thousands of data concentrator units simultaneously, and also handle data coming in from other things like direct reads. They should act as a metadata warehouse and a metadata management system. They should also convert data into enterprise-ready information and route it to where it's necessary. They should provide management reports, and they should provide network management and monitoring on things like cybersecurity, attacks, downtimes, etc. The DCUs can handle a lot of the data locally, and so we should push some of the functionality into those away from the head-end systems, so that they can provide far more data handling capability and reducing the load on the backhaul networks. One of the comments we need to make here is that in our concept, the DCU acts as a head-end system. The head-end system acts as a data warehouse. So how do we use the data within the enterprise? If you remember this part of the diagram from a previous diagram when we were talking about generation and data flows, you see we have lots of different components, and typically each department has its own applications. In the past, historically, they were actually purchased without any reference to what other departments were doing. And so we've got all these different applications with their own islands of information. As we move into the smart grid, we have some enabling technologies such as communications and GIS, and so we can separate these enabling technologies to support the enterprise as a whole. But the point here is that as we move forward, all of the applications, including enabling and departmental, should speak the same language where possible. A couple of initiatives around the world seek to point or push utilities towards a standard, and in Europe it's one called the CIM, Common Interface Model. Very similar one in America, but slightly different, is Multispeak. Basically does the same thing. But what we need also within the enterprise is the concept of an asset services repository. And here we're not talking about physical assets, we're talking about data assets. And all of those assets should be made available to any department on demand. So with those assets in place, we then can support the need for new corporate-wide applications such as business intelligence, data mining and analytics. And we also need to ensure that throughout the enterprise there are no silos of data. In other words, people handling similar data but different versions, different points in time that are not in sync. So what we've got to be careful of here is that data will become the utility's most valuable asset, and we have to manage it as a common entity. Now let's briefly talk about delivery of data to the customers or consumers. This is a fairly new concept for a lot of utilities, but consumers are expecting a lot of data to be delivered to their mobile devices. And here we're not just talking about Twitter feeds or locational information, we're talking about billing information, usage information, etc. They already expect this kind of facility from other industries, particularly the banks and telecoms. And some utilities, as I say, are just beginning to realise the value of sharing more data with the consumers. Better provision of data empowers consumers and enables them to make better, more informed choices. So they can use energy more efficiently, they can change their consumption patterns from times when energy is more expensive, they can provide feedback to the utility on consumption, and the utilities can also benefit from pushing data to consumers in that they can have more consumer satisfaction and they can enable lower cost to deliver data. So instead of stuffing envelopes and putting them through the mail, they can be delivered cheaply over the internet. They can also derive further benefits throughout the value chains with concepts like peak shaving to make more efficient use of the infrastructure that's already in place. So the utilities are beginning to realize that to share data is to become part of the solution, and everybody benefits. Very briefly, what about some of the concerns? These fall into two camps. Firstly, for the utilities, we have concerns regarding interoperability. How will all these devices talk to each other? How do we handle cybersecurity and attacks from malicious points? How do we overcome the problems of data overload? How do we work on problems of obsolescence, premature obsolescence? And what about the costs of all of these systems? From the consumer's point of view, they're concerned on other things such as privacy of personal data, ease of use of the systems and information. They're also concerned about other things like nuisance information. They don't want to be getting junk emails delivered through their handsets just because they sign up to get more information from the utility. But anyway, there are some concerns. There are some techniques to mitigate them, and if we put the effort in, then the rewards will justify that effort. So finally, just let me draw some conclusions. Firstly, the utilities need to plan for an avalanche of data, and they have to make use of that data and turn it into pertinent information and deliver it to where it's needed. It will take a lot of effort, but in the end it will pay dividends to all stakeholders. We looked at the need to move data only as and when it's required to keep the load off the systems. So we need to leverage the power of distributed processing. There are some critical factors that we must take into account, and that is that the utilities must avoid vendor lock-in. In other words, locking into one technology that will cost them too much money in the long run. They need to adopt standards to achieve that. They need to take security seriously. They need to take privacy seriously. They need to be flexible in system design and implementation, because we're only just embarking on this smart grid revolution, and to shake it out will take tens of years, if not multiple decades. And they have to work with industry experts and other industry peers to find out what is best in the industry at a given point in time and what are the experiences. And so if we turn data into pertinent information, it's valuable, and if we empower the consumers, it benefits both the consumer and the utility. So that was a very brief high-level view on some of the concepts of managing data within an electrical utility. I'm sure you may have some questions, you may even have some comments. If you do, these can be addressed to wanttoknow@screamingpower.com, or you can get information on any of the other products and services that we provide. I hope you found the video informative and useful, and hope to see you again, more videos on this topic. Thank you for looking.